So we've seen a few inclusions already, but inclusions are very useful in particularly in metamorphic and structural sections. Also, it can be used in igneous for looking at crystal growth. And there are a few terms here. So we've talked about porphyroblasts, which are metamorphic minerals which have grown large in a particular rock. And a particular type of porphyroblast is called a poikiloblast, which is just a porphyroblast which is full of crystals, rather like this strikingly yellow staurolite here. So the staurolite, the name that we used to have on some schools for this, was Swiss cheese mineral, because it's strikingly yellow like Swiss cheese, but also usually full of holes. So that's a nice way of remembering that. One of the things to notice about this, though, is not just that it's got lots of inclusions, but that those inclusions are more or less random inside the staurolite. I don't think I can really see much alignment in them at all. And that's true in the matrix as well. You can't see any real alignment or foliation or fabric in the matrix. So that suggests a rock which has just sat there without being deformed at all and has grown metamorphic minerals like this staurolite just purely in a static, if you like, non-tectonic environment. It's just been buried and heated. And these are very similar poikiloblasts again, so they look pretty much undeformed themselves. The matrix of the rock looks pretty much undeformed. Well, there might be a very, very faint fabric running north-south, but it's really, really subtle. I don't know if I'd even be sure of that. And again, the inclusions within those poikiloblasts are not really aligned. So far all they're telling you is something about the way that the crystals grew, and that these probably grew after, quite late on in this rock's history, and just overgrew the original ground mass. But at other times you do start to see some orientation of the inclusions within the crystal. In this garnet, for example, there is a very faint alignment of the crystals, the inclusions within it, up here. Down here, around the crosshairs, I don't think there is. There's actually virtually no alignment at all. They're quite random. But up here, I would say there's a very, very faint alignment running kind of northwest, southeast-ish, I guess, an alignment of those inclusion grains there. That's quite faint in that crystal. There's no alignment in the core area here, but if you look in the matrix, you can see that there is also an alignment, a foliation, a fabric running northwest to southeast again, so in this direction. And I've outlined that here with these dashed green lines. So you've got a garnet crystal which has grown. You've got an external fabric which has wrapped around it. You can see that that fabric isn't straight. It's been deflected around the garnet. You can think of it as being kind of sheets of paper that have kind of you've then scrunched over the garnet, and it's bent round the garnet, which is a rigid crystal. But then in the inclusions here tell you that that garnet must have kept on. It started growing when the rock had no fabric, because those inclusions in the core, when the garnet started growing, are randomly oriented, no orientation. But as it grew outwards, this garnet started growing over crystals that were aligned, quite weakly aligned, but there is some sort of alignment there, some sort of foliation. So you've got a garnet that has grown from a time where before deformation and through into a time when the rock was deforming. And so that garnet we can call synkinematic or syntectonic. So it's grown during deformation. And that really shows the value of these inclusion trails within minerals. So here we've got a rather more extreme example, and I've shown this in both plane and cross-polarized light here to emphasize the difference. So similar garnet mica schist, it has an external fabric here which I've picked out with the green dashed lines here, and again that's sort of bent over the garnet in a rather odd way. And the schist has a banding too, so it has mica-rich portions at the top and bottom here, and then a much more quartz-rich band in the middle. But the garnet has inclusions which run almost 90 degrees to the external fabric, and I picked that out with a red dashed line here. So This fabric, the internal fabric, is clearly different from the external fabric. The garnet must have grown over this fabric when the fabric was running northeast-southwest, and since then the rock has deformed. Let's imagine that the garnet stayed still during this whole process. As it grew, it just grew in situ, and after it stopped growing, the whole rock was deformed, and the fabric in the rock was turned through 90 degrees. So all the minerals outside the garnet recrystallized into a different orientation. So you've got an internal fabric, first deformation event, and then the garnet growing over that, and then a second deformation event. Yeah, so if you have a garnet with no inclusions, but the external fabric is wrapped around it, the micas are wrapped around the garnet, then the only thing you can say for certain is that the garnet must have been there before some of the deformation, because the micas have been bent around and deformed around that rigid garnet. You can't say much more than that. So there are a lot of other possibilities. The garnet might have grown over a very long period, but it certainly can't have grown post-tectonically, and it must have grown at least partly pre-tectonically. But it could easily also have grown syntectonically, but you can't be sure of that. There's no evidence. And that's often the difficulty with these things, is that it is difficult to pick up exactly what you can say and where your evidence is somewhat lacking. But in the case you've described there, that would you could certainly say it was pre-tectonic, but you'd have to say that it might also have been syntectonic, but there's no evidence one way or the other. So looking again at inclusions, this is a different crystal here. We've got a large plagioclase crystal here, which is showing grey in cross-polarized light. And here you've got inclusion trails, very fine inclusion trails within the plagioclase. These are probably fine graphite. So the inclusion trails are oblique to the external fabric, which is picked out with these yellow dashed lines here. That's a mica fabric. So it's a different fabric. The other thing you can say about this is that it's curved. The internal fabric in the plagioclase here is curved. And that's really good evidence for the plagioclase having grown syntectonically. Because if the inclusion trail is straight, then the mineral could have just grown straight over a straight fabric completely after the deformation. But in this case, if the inclusion trail is curved, then almost always that indicates that it is syntectonic. Because what it tells you is that as that crystal was growing from its core to its rim, the orientation of the fabric over which it was growing has changed or is changing during the growth. And so that means that deformation was going on at the same time as the crystal was growing, so the crystal must be syntectonic. So again, curved inclusion trails are really nice evidence for that.